This PowerPoint is produced for the AMS Weather Studies course, WE 101 at Mohawk Valley Community College, and this is Chapter 5, and we're going to be discussing air pressure. One of the questions that we can ask is basically, how do we define air pressure? What are the properties of air pressure? How do we measure air pressure? What are some of the spatial and temporal or time variations in air pressures? We have to talk about some gas laws, so there's some science involved in this. And we'll end up talking about cooling and warming based on expansion of air masses. We know from previous chapters that molecules of air are moving rapidly in all directions, and that these molecules, as anything, has mass, and therefore they exert a force on the surface of the object that it comes in contact with. Air pressure represents a measure of that force per unit surface area. And again, a force is nothing more than a push or pull on an object, and is computed by the mass multiplied by the acceleration. So the total air pressure is the cumulative force of a multitude of molecules which are colliding with the unit surface area of any object that is in contact with the air itself. Since air is made up of a number of different types of gases, we have to be aware that there are different contributors to this air pressure itself. Each gaseous component of the air contributes to the total air pressure as described in something known as Dalton's law of partial pressure. That is, because air is made up of nitrogen and oxygen and hydrogen, we really have to appreciate this partial pressure law. Dalton's law states that total pressure exerted by mixtures of gases is the sum of the pressures produced by each of the individual gases involved. That is, stated another way, each gas exerts a pressure as though it were the only gas present. So the pressure produced by the gas molecules in air depend on a couple of things. One, the mass of the molecule, and two, the kinetic molecular activity, or how fast things are moving. So we can say that the pressure at any point within the atmosphere is equal to the weight per unit area of the atmosphere above that point. So weight basically equals mass times how much force is being pulled on that, or what we call gravity. Now if we did the calculations, we would find that the average air pressure, that's average air pressure at sea level, is approximately 14.7 pounds per square inch. So think of the number of square inches you have, say, on your body, and you can multiply those number of square inches by 14.7 pounds, and you come up with a very, very large number. Now, why don't we squeeze into this small little structure if we have all this weight bearing down on us? Or why doesn't a roof collapse with the significant amount of weight that's pressing down on that? The reason is that basically air pressure at any point is always in all directions, up, down, and sideways. So air is pushing up, say from under a roof, as well as down from above the roof. So air pressure within the house or within your body exactly counterbalances the air pressure outside, so the net air pressure acting on your body or on the roof is basically zero. So the idea is that at any point in a gas or a mixture of gases, pressure is exerted equally in all directions. It's important for us to be able to measure air pressure because we know that air pressure changes, and with that comes some very, very distinct effects relative to weather formation. And the instrument that we're going to use, or it has been used for 300, 400, 500 years, is something called a barometer. And here's a look at a typical barometer known as a mercury barometer, which was actually designed in 1643 by Torricelli. We know from past experience and experiments that the average air pressure at sea level will support a mercury column in the tube to a height of about 760 millimeters, which is about 29.92 inches. Now those two numbers will be important to us as we will see down the road. The height of the mercury column will change as the air pressure changes, and that's how we can determine changes in air pressure using this mercury barometer. You can appreciate that a mercury barometer probably isn't very portable, so to that end there was designed a different type of barometer, a non-liquid barometer called an aneroid barometer. Although it's more portable, it is really not as precise as a mercury barometer, which for our purposes and most purposes is not critical. You can see the design of the barometer. It's really nothing more than a series of chambers and springs with pivot points that read on a scale, and with changes in pressure there is the movement of the needle through these various points to give us some change as far as barometric pressure is concerned. Generally, taking air pressure at any single moment in time is really not that important to us. What we want to see is the air pressure tendency, or the pressure of change in air pressure over a specific time interval, for instance generally several hours. We know that rising air pressure is basically a situation which will bring about continued or clearing weather, whereas falling air pressure generally signals the approach of some sort of storm. A simple way of seeing that air pressure temperature is simply linking an aneroid barometer to a drum with various graphs associated with it, and this particular instrument is called a barograph, and it provides a continuous trace of air pressure variations with time, and it's fairly sophisticated in terms of bringing about changes that we can see visually. If you were watching the Weather Channel and they were talking about air pressure readings, they would generally report these in millimeters or inches of mercury. However, scientifically it's more appropriate to basically measure these things in something called a unit of pressure, or the Pascal. We know that the unit pressure pascals is basically standard metric unit of pressure. However, U.S. meteorologists traditionally designate air pressure in millibars, or MB units, where 1 millibar equals 1 HPA or 100 PA. In turn, 1 millibar is equivalent to 0.02953 inches of mercury. Well, if this isn't confusing, I don't know what is. However, I think what you have to appreciate is we're probably talking about millibars generally, and the millibars generally average worldwide 970 to 140 millibars. Very low pressure, relatively high pressure. You can see the numbers for the lowest and the highest ever recorded, so we have history relative to millibars and high and low pressure. This table gives us the conversion factors for units of air pressure, and I certainly wouldn't expect you to sit there and memorize all of these, and that would be ridiculous because you can always look it up. However, I think keeping in mind the idea of this 970 to 1040 millibars is fairly critical in terms of our appreciation of high and low air mass. I think one of the things we can appreciate is that there are variations in air pressure that occur, and one of the ways they occur is with altitude. We know from inflating a bicycle tire that air is compressible, that the volume and density of air can be variable. We can have the same amount of air either in a bicycle tube or outside, but there is some difference in the pressure relative to that. The pressure of gravity compresses the atmosphere so that the maximum air density is basically, as you would expect, at the Earth's surface. What that means is basically gas molecules are closest to one another at the Earth's surface, and as we increase with altitude, the air molecules become farther and farther apart. In fact, at about 11 miles above the Earth's surface, they're only about the air density is only about 10% of the air density that we find at sea level. Therefore, going up in the atmosphere, obviously you're going to have fewer air molecules, and that's why it's more difficult to breathe because of the fewer molecules of oxygen associated with the same volume of air. So to put it very succinctly, the number of gas molecules per unit volume is the number density of air, which decreases with altitude. The thinning of the air is so rapid within the lower atmosphere that at an altitude of about 4 miles, air density is only about 50% of its average sea level, valued at about 11 miles, as we said, is about 10%. So this particular graph shows us that with the thinning of air, we also see a decline in air pressure. And because air is compressible, the rate of air pressure drops with altitude, and as we can see, it is not uniform. It's greatest at the Earth's surface and becomes more gradual aloft, as shown here. In the lower troposphere, air pressure usually drops by roughly 1 millibar for every 10 meters, or about 30 feet, of ascent. However, as we'll see in a few minutes, the actual rate depends upon the air temperature and also the humidity of that particular mass. This table shows the changes in altitude, temperature, and pressure, and we can see very definitively how it changes as we increase the altitude. We can see that there is a distinct change in pressure and temperature as we increase the altitude. You'll notice that the table is defined as a standard atmosphere, and that's important for us to appreciate. These vertical profiles of average air pressure and temperature are based on this thing we call the standard atmosphere, which is a model of the real atmosphere which was initially used to assess aircraft performance. The standard atmosphere is the state of the atmosphere averaged for all latitudes and all seasons, and is fixed at a sea level air temperature of 15 degrees centigrade or 59 degrees Fahrenheit and a pressure of 1013 millibars or 29.92 inches of mercury. Now we need to standardize this to the standard atmosphere, because if we didn't, all the pressures would be based on altitude, really not changes in pressures at specific areas. Think of this. If a weather station in Denver, which is somewhere around 5,000 feet and has an average pressure of 24.6 mercury and about 12.1 pounds per square inch, compared with a normal 14.7 that we look at. And we looked at Denver versus San Francisco, which is at sea level, which would be 29.92 inches of mercury and 14.7 psi. So if we looked at those and we ran isobars as we do when we make weather maps, we would find out that the weather in Denver is always going to be at a relatively low pressure compared to, say, San Francisco. And that means that without adjusting for a common reference, you would think that Denver is always going to have a very low pressure. We know that low pressure weather means stormy weather or inclement types of weather, and we know that that's not true. So by standardizing this, we are no longer dealing with altitude, we're dealing with the actual change in the pressures between places on the map in the United States or wherever we're doing the pressure. Now, even though vertical changes in air pressure are important, generally we're more interested in the horizontal variations in air pressure because they're much more pertinent to weather forecasting. Again, we don't want air pressures to be related to elevation of the land. So again, weather observers determine an equivalent sea level air pressure value, and that is for stations located above sea level. They adjust the local air pressure readings to approximately what the air pressure would be if the station were located at sea level. With this reduction to sea level, when this is carried out everywhere, air pressure is observed to vary from one place to another and to fluctuate from day to day and even from hour to hour. Now, these air pressure readings reduced to sea level, which range in value from one place to another, we can see by this particular map that the range is not very great, significantly less than the rate at which air pressure drops with altitude. Except in various things like tornadoes or intense hurricanes, the horizontal pressure gradient at sea level rarely exceeds 3 millibars per 125 miles or so, which is equivalent to the vertical change in air pressure experienced in the lowest 30 meters or 100 feet of the troposphere. But these very, very small horizontal changes in surface air pressure can be accompanied by significant changes in weather. Talking about horizontal variations, we know that rising air temperature, if we think about it kinetically, is an increase in the rate of molecular motion. And if we think about something like a closed container, when we heat up that container, air exerts more pressure on the sides of the container, but the density of the container does not change because no air has been added or removed. But we can increase the molecular motion of those particular molecules. By contrast, except for the Earth's surface, the atmosphere is not confined. So air is free to expand and contract. That is, in the atmosphere, air density tends to be variable. So within the atmosphere, when air is heated, either by radiation, conduction, convection, or latent changes in the water, air density usually decreases because of the activity of the heated molecules. Molecules are farther apart, farther from their neighbors, and that spacing increases, which means density is changed. As a column of air is heated, the number of molecules per unit volume decreases. That is, air density decreases as, say, within this hot air balloon that we see here. A lowered total mass in the column would exert less pressure on the Earth's surface. So understanding the greater density of cold air versus warm air at the same pressure, we can see the effect that might occur because of the rate at which the air pressure drops with increasing altitude. Air pressure drops more rapidly with altitude within a cold, that is a denser column of air, than a warm or less dense column of air. Besides temperature, humidity also has an effect on air pressure. Increasing humidity affects air density in the same way as rising air temperature. That is, the greater the concentration of water vapor, the less dense is the air. Now, this statement may be contrary to what you've heard, that humid air is heavier than dry air. But basically, although hot, muggy air may weigh heavily on a person's disposition, humid air is less dense than dry air at the same temperature and pressure. That is, muggy air is lighter than drier air. Now, this is because of something known as Avogadro's law. And this law implies that when water molecules enter the atmosphere as a vapor, water vapor, while the temperature and pressure of the air remains constant, the water molecules displace other gas molecules, primarily nitrogen and oxygen, because those are the two dominant components of air. So if we're kicking out these high molecular weight molecules and replace them with a lower weight molecular molecule of water, obviously the air is going to be lighter. So to sum up to some degree the horizontal variations in air pressure, we can say definitively that cold, dry air masses are the densest, and they generally produce the higher surface pressures. Warm, dry air masses exert higher pressure than warm, humid air masses. And pressure differences created horizontal pressure gradients, and they cause cold and warm air advection. And remember, advection simply means transporting something from one region to another. And meteorologists are really most interested in the advection of variables like temperature and moisture. When we assess advection on weather maps, it's dependent upon two factors, both being related to wind, the strength and the angle of the wind relative to the lines of values of the variables being advected. The strongest advection occurs when the winds are oriented perpendicularly, that is 90 degrees, relative to the isolines that we're looking at. No advection occurs if the winds are parallel to those lines. So our conclusion is that local conditions and air mass advection can really have an influence on air pressure, and we need to keep that in mind, especially in terms of horizontal variations in air pressure. So speaking of winds, supposing that at the Earth's surface horizontal winds blow away from the column of air as we see here. This is an example of what we call diverging winds. Concurrently, we can have horizontal winds that may be above the diverging that are blowing toward the column. And this situation we talk about horizontal convergence or converging winds. As described here, if more air diverges at the surface than converges aloft, air density and surface air pressure obviously is going to decrease. And the opposite is true if we do the reverse. You all should be familiar with highs and lows from the very first lab that you did, talking about intervals between these things which we call isobars. What does a high system mean? What does a low system mean? So I won't spend much time on this at this point. Up to now we've been describing the state of the atmosphere based on basically three things: temperature, pressure, and density. These important properties of air are known collectively as the variable state, or the variables of state. These three variables of state are interrelated through what is known as the gas law. Although the gas law was derived for a single ideal gas, the law provides a reasonably accurate description of the behavior of this mixture of gases, which we call air. Now, an ideal gas in a confined volume follows two laws exactly, Charles' law and Boyle's law, whereas a real gas, the one we're talking about in terms of the atmosphere, only approximates these laws as they will predict various situations. Let's take a quick look at the two laws. Charles' law states that with constant pressure and temperature, an ideal gas is inversely proportional to the density of the gas. That is, as we heat a sample of gas, the gas expands and its density decreases. So that's where this inversely proportional situation comes in. According to Boyle's law, when the temperature is held constant, the pressure and density of an ideal gas is directly proportional. That is, as a pressure on a sample of ideal gas increases, its volume decreases and its density increases. So we take these two laws and we put them together, the Charles' law and Boyle's law, and they are combined into what is known as the ideal gas law. As we noted earlier in the chapter, air pressure always decreases with increasing altitude within the atmosphere. One of the more important consequences of the decline of air pressure with altitude is that it will expand or compress as they move up and down. So as an air parcel ascends and expands, its temperature drops. As an air parcel descends and is compressed, its air temperature rises. As we'll see in the next chapter, this expansional cooling and compressional warming will be factors in the development of clouds or the dissipation of clouds. One of the ways in which you may be familiar with expansional cooling is if you've ever opened the valve of a bicycle or tire or automobile tire and put your hand over the valve as it's releasing air. Air within that tire, which is probably under much greater pressure than the atmospheric pressure outside, is released, and air, which is moving through that open tire valve into the atmosphere, does work as it pushes aside that air formerly occupied by the volume into which it expands. Work requires energy, and energy is used in that work of expansion is drawn from the internal energy of the air, so the temperature of the expanding air drops. Because of that situation, that is why air coming out of a compressed component generally feels relatively cool. As the pressure on any sort of air parcel increases, the air parcel is compressed, and the temperature rises, and that's known as compressional warming. An example of that is the heating of the cylinder wall in a tire pump as air is pumped into that tire. If you feel the tire pump after you have put air into the tire itself, it will feel warm. That's because the work of the compressing air is converted into heat. As an air parcel descends within the atmosphere, as an air parcel drops, it is compressed, molecules become closer together because of the increased surrounding pressure, and the temperature begins to rise. Let's go back to the previous slide for a moment and talk about the law of energy conservation, which is also known as the first law of thermodynamics. And this applies to our expansional cooling and compressional warming of air parcels as they move through the atmosphere. Now, according to this law, we have to account for all the original energy in any physical or biological system, regardless of the energy transformation that takes place. In other words, we have to know what's happening to the heat or whatever in this particular situation. So the heat energy that's gained by an air parcel can either be added to the parcel's internal energy or is used to do work on the parcel. Conversely, the heat energy that is released by an air parcel is either subtracted from the internal energy of the parcel or is the consequence of the parcel doing work on its surroundings. So we can appreciate that a change in the internal energy of an air parcel is directly proportional to the change in the temperature of the parcel. A transfer of heat to the parcel raises the temperature, whereas a transfer of heat from the parcel is going to lower its temperature. With our understanding of this law of energy conservation, or the first thermodynamic law, we can apply this to air parcels moving vertically within the atmosphere. But we have to talk about something called the adiabatic process. And during the adiabatic process, there is no heat exchange between an air parcel and its surroundings. That is, while ascending or descending within an atmosphere, the air parcel is neither heated nor cooled by radiation, conduction, phase changes of water, or mixing with the environment. The temperature of an ascending or descending unsaturated air parcel changes in response to only two things: expansion or compression of that air parcel. Now, one of the things we talk about is something called the lapse rate. And the lapse rate is a change in the atmospheric variable with height. And generally, the atmospheric variable that we're talking about in terms of lapse rate is the temperature. Again, keeping in mind that as air ascends, there is cooling, the dry adiabatic lapse rate, this dry designation, is a bit misleading because ascending and descending air parcels always contain some water vapor. The dry adiabatic lapse rate applies to any parcel that is not saturated with water vapor. That dry lapse rate is approximately 5.5 degrees per 1,000 feet of atmosphere change. So the dry adiabatic lapse rate describes the temperature change of unsaturated air as it moves either up and or down within the atmosphere, and that temperature is generally as described in this particular PowerPoint slide. Now, once these rising parcels reach a relative humidity of 100%, that is saturation, latent heat now becomes a situation we have to consider. With these phase changes of water, latent heat is released to the environment during ongoing condensation or deposition, and consequently we have this phase change partially countering the expansional cooling. So a saturated cloudy air, these parcels are going to cool at a lower rate than ascending unsaturated clear air parcels. Rising saturated air parcels cool at the moist adiabatic lapse rate. As you can see, this moist adiabatic lapse rate is cooler than the dry adiabatic lapse rate because of the latent heat, which partially counters this expansional cooling. These particular graphics give you a comparison of dry and moist adiabatic lapse rates, and they describe the difference in temperature changes with the difference in levels of condensation or moisture in the air. Thus, different parcels of air with different temperatures and different moistures can have significantly interesting effects on weather in the atmosphere, and specifically in the troposphere area, whereby cooling and heating rates of air parcels are based not only on altitude but on the amount of moisture that are found within these air parcels themselves. So now we have a basic understanding and maybe a working definition of air pressure, and we have examined the causes of both the spatial and time variations in air pressure within the Earth atmosphere system. One of the important things to remember is the range of air temperature and air pressures in the Earth atmosphere system allows water to exist in all three phases,